He is a PhD graduate from University of California, Berkeley. He will be speaking on 2D nanomaterials, their synthesis and characterization. So now I request Professor Hitao to please take over the mic.
Thank you. Just a quick audio check. Can colleagues online hear me all right? Online colleagues, can you hear me? Okay, thank you. All right, now I'm going to share my screen. Colleagues on Zoom, can you see my screen all right? Thank you. All right. Oh, okay. So first of all, I want to thank the organizers. All right. First of all, I want to thank the organizers and also the Indian government for providing me this opportunity of joining everybody here for this exciting program. As I shared with you a bit earlier, I will talk about a number of things, 2D materials, carbon materials, and the DNA nanotechnology. Those are the research topics of my interest in the past 15 years or so. I will give two types of talks. One is more introduction, probably more suitable for undergraduate students. Another is more research-intensive talk that probably will trigger interest more from graduate students, PhD candidates, or faculty members. But also, to give me a sense of who the audiences are, can you raise your hand if you are an undergraduate student? Undergraduate student? Wow. I am impressed. Thank you. Can you raise your hand if you are a postgraduate student, either a master or a PhD student? Thank you so much. Thank you. What about faculty members? Any discipline? Thank you. Thank you very much. All right, and last question. Can you raise your hand if you never heard of 2D materials before? Or raise your hand if you are not familiar with 2D material. Okay. Raise your hand if you are very familiar with 2D material. Okay. I guess a lot of people are somewhere in the middle. Okay. All right. Thank you. That's very helpful for me to calibrate myself because an important task of any presentation is for the whoever delivering the lecture to know who the audiences are. So now I have a pretty good understanding. All right. Thank you. So to give you a very brief introduction of where I come from, here I show a map of the United States. And where is Pittsburgh? Pittsburgh is in the eastern part of the state, in the state of Pennsylvania. We're on the west side of Pennsylvania. And on the top, there's also, you also see a picture of a tall building. That building is called Cathedral of Learning. It's actually the highest academic building in North America. And in this building, there are a lot of classrooms, and they are decorated according to traditions of many different nations. And there is a room of India. And those rooms are made possible by donation of local immigrants. So local Indian immigrants donate money to make a Indian room, local Chinese population donate room, make a Chinese room, so on and so forth. Why they made that? Because when the building was built in the 1930s, they ran out of money. So they have to find creative ways to raise money from the local community, and that was one of the tricks they figured out back in 1930s. But it worked very well. Now it's a tourist attraction because we have about, I think, 20, 30 different rooms. We call them nationality rooms. So there's UK, there's France, all kinds of countries you can think about. Chances are there's a nationality room. So if you get a chance to visit Pittsburgh, I encourage you to keep that in mind and take a quick tour to that building. Okay? Again, that's called Cathedral of Learning. And there are a lot of classrooms there. There are a lot of administrative offices. Our chancellor's office is at the top of the building, okay, as you may imagine. All right. Also, a bit about myself. I started as an organic chemist when I was an undergraduate student. I grew up in China. I went to a college called University of Science and Technology of China. It's a very intense STEM school. I took a lot of math class, a lot of physics class, a lot of class I don't know why I take them, but I took them because I have to. Now they turn out to be intensely beneficial because they prepare me well. Okay. So undergraduate students, when you are struggling with certain class you don't want to take, think about what my experience can tell you. Okay. So in 2001, I went to United States to take graduate school, and 2007 I graduated with a PhD at UC Berkeley. In my PhD, I tried to turn myself into a physical chemist because chances may have it I have to join a physical chemist group. I was the only person with organic chemistry background in the group. But again, that change of track turned out to be very beneficial for me because now, at that time I brought in my experience and knowledge of organic chemist, thinking everything from mechanistic side of view. I brought that to studying nanomaterial synthesis. And that turned out to be very, very fruitful. So we published a lot of interesting papers. In 2007, I went to Columbia. I did a 3-year postdoc with 2 advisors, Colin Knuckles and Lou Bruce. You may recognize Lou Bruce's name. He was one of the Nobel Prize winners 2 years ago. Unfortunately, Paul Asados, my PhD advisor, he didn't win Nobel Prize. He should have been one of them, but he didn't. 2010, I went to University of Pittsburgh. I started my independent career. Now again, I made a career transition there because remember I trained as an organic chemist. I turned myself into a physical chemist when I was at Berkeley. And at Pitt, University of Pittsburgh, we call it Pitt, I started to do mostly materials research. So again, I'm learning something but doing something very different. But again, it's a very helpful and a very productive transition for me. I took all my trainings as a physical chemist and organic chemist. I started to incorporate those thinking into material science research. I find that very, very helpful. I encourage you to think about those career transitions in your future. Some of you will graduate with a bachelor's degree, master's degree, and PhD. Please do not be afraid of make a change, explore something new. There's always this tremendous benefit of bringing old knowledge and experience into a new field. This cross-pollination, so to speak, has been a key feature of all the field I can think of where people are successful. They always, put different things together. All right, I see some. Can colleagues online hear me now? I see some comment that some colleagues cannot hear anything. Okay, I'll assume things are going well then. All right, now on the scientific part, as I said, I'll do a more introduction lecture, and then this will be one of them. I'll talk very briefly on 2D materials, very generic. Hopefully, will get you interested in this new class of material. And then in the afternoon, I'll talk more research results from my own lab. There'll be more technical. This one will be, you can think it more as an introductory course of a material science. Hopefully, if you are not familiar with this material, it will get you interested, and hopefully will get you interested enough to continue listening to my other lectures. Hopefully it will not scare you off, and that's my hope. Okay. This will be very interactive. I know it's a large classroom, a lot of people, but the key point here is communication. Not only communication from me to you, but also communication from you to me. There's no stupid question. There's only stupid answer. So if you have any question, feel free to raise your hand. Interrupt me anytime. My purpose here is to share what I learned. A lot of things I share today is actually pretty new to me as well. It's a very good opportunity for me to refresh my memory and to refresh my my literature reading. A lot of those contents are taken from, pretty much all of them are taken from literature. So there are a lot of figures I'm going to explain to you. If you don't understand what I'm talking about, then it is my fault. That's the position you should take on, when you make a presentation. If your audience has a question, if they are confused, it's because you are not doing a good job. So I hope you can help me to do a good job by asking questions. Okay. Let me just. Okay. All right. So admin, please mute Nassim. All right. Okay. All right. So I want to, in this one, I'm going to talk about 2D material, and this slide shows where it started. You may have heard this Nobel Prize given to 2D material back in 2010. Two physicists and some strange physicists, okay, not material scientist, not chemist, physicist. Two physicists got the Nobel Prize for discovering a new class of material called graphene. Okay, those two people are Andrew Geim and Konstantin Novoselov. Okay, both are scientists working in the UK at that time. What they discovered is a material called graphene, which is a single layer of graphite. If you're familiar with the structure of graphite, it's a layer compound, carbon atoms in a honeycomb structure. Okay, all right. There's some technical adjustment. On the left-hand side is a optical photograph, so a picture taken through a microscope, and it shows this pink, purplish flake. Okay, and you see the size is about 20 micrometers. So this is a pretty small piece. Okay, and this is a few-layer graphene, so not a single layer, but number of layers. Exactly how many layers, they actually don't know, but they all know it's pretty thin. Okay. And this is deposited on a silicon wafer with a thin layer of silicon oxide, about 270 to 300 nanometer thick of silicon oxide. Now 1 nanometer is 10 to the minus 9, so 300 nanometer is about 0.3 micrometer. Again, it's pretty small thickness. Now that number turns out to be important, as I will explain in a bit later. Okay. Now this Nobel Prize triggered, even before the Nobel Prize is given, there's a huge wave of interest in understanding 2D materials. And why it's called 2D, as you see in this graph, is a sheet. Okay, so it's two-dimensional material. Exactly what kind of material, there's a lot of options there. And people got very interested in this for all kinds of reasons, not only because you got Nobel Prize, but because of a lot of other reasons. And I'm going to list some of them here. Okay, all right, so this is a very interesting class of material because it is, in theory, the thinnest material possible. In the case of graphene, for example, is composed of just a single layer of atoms. The single layer of atom make a two-dimensional network. You cannot go any thinner. Now, why that is relevant? Because there are a lot of applications they would like very thin material. For example, transparent conductor. Okay. Think about solar cell. You want solar light to come into a material, generate electricity, but also have that electricity collected by electrode. And the ideal structure there would be some kind of transparent conductor. If you want it to be transparent, you better make it thin. So in this case, thin is good. Nanoelectronics, why that is relevant? Because you want to make the structure as smaller as possible. What is the smallest structure you can make? A single atom thick. That's, again, the ultimate thickness and smallest device architecture you can think of. In some other applications, you want very high surface area. For example, sensing. As a sensor, you want to capture as much analyte as possible and having the analyte to impact as much change of material property as possible. So in those cases, you want high surface to volume ratio, and there's no possible way to go beyond single atom thickness. In that case, all the atoms will be impacted by the environment. So that would be a pathway to give you maximum sensing output. All right, it's also an interesting class of material because a lot of properties, material properties also change as you make them thinner. So there are properties that you find in bulk that disappear when you make them into single thickness. There are also properties that do not have, you cannot find in bulk. They start to show up when you make them thinner. One example would be molybdenum disulfide. This is a semiconductor material. In the bulk, for example, it doesn't fluoresce. You shine UV light, it doesn't give you visible light. But once you make it into a single atom layer thin, it becomes a fluorescent material. So you can generate new properties by using the same kind of chemical composition, but simply by changing the architecture, you can develop new applications. If I, going down the list, you'll find there's this tremendous application because of the nanoscale architecture. High surface area, very small thickness, so on and so forth. And above all, there's also very broad material of material composition you can think of. There's carbon. There's so-called transition metal dichalcogenide, so-called TMDs. This is a large collection of M, so metal chalcogenide 2, so MS2, MSE2, so on and so forth. Boron nitride, a lot of metals. So if you look at the periodic table, chances are if you can get a layered structure in the bulk, you can probably make them into single atom thick. So all kinds of choices in terms of material, in terms of architecture, in terms of application, that triggered all this huge interest in 2D materials. So today I'm gonna give you 3 out there and how they are made and what kind of applications people have developed them for. Again, those are very introduction level material, and hopefully the goal is to trigger interest so that you can stay here and listen to my talk in the afternoon. Okay. All right, so The first class of example is graphene. So this is, again, the material that produced the Nobel Prize in 2010. Okay, there's some Zoom issue. I think we lost internet connection just now. So I'll let it recover. Sorry about that. I think microphone is working, but Zoom is out. No, that is. Sorry about that. You can close and rejoin, but I think Wi-Fi is very out. Yeah. All right, we should be back online anytime. I'm still connecting to Zoom in case you're curious. All right, we're on Zoom. I think should I join? Should I join? Okay. All right. Okay. Colleagues on Zoom, sorry we had some technical challenge. Can you hear me now? I think we're waiting for the projection. Okay. All right. Should I resume? Okay. All right. Sorry about the interruption. There's some power issue that interrupted the Zoom session. Wait, yeah. Okay. Should we do it now? Okay. All right. Okay. Okay. All right. Yeah. Yeah. Sorry, I need to. Okay. Should I disconnect from the Zoom? Okay. All right. Thank you. I'll copy. So we are making some adjustment to the online synthesis. Yes. Okay. I'll copy. Okay. All right. See if that works. I disconnect from Zoom. Okay. Well, wait for the power to come back.
also.
Hello, hello.
They are slightly different format. So the one on the right, what you see is a hole on which the hole is pretty small, about 50 micrometer in size. And in this hole, there's
keep talking, and I'll describe what I see on my screen. And if I'm doing a good job, you all know exactly what I'm saying. If I'm not doing a good job, you should ask me questions. Okay, so on the other side, you may recall there are two more images. And now we work, okay. Every year we have admit about 40 students, and they take about 5 years and a half to graduate. So we have a steady state population of about 200 graduate students. Again, it's a pretty large program. In the undergraduate level, we have about 150 just formed. We have a union for graduate students. All graduate students on campus. And one of their big job goal is to increase the standard. So by increasing probably about $45,000 a year in a couple of years. So if that interests you, keep that in mind. Okay, so what we are looking for in the application, we look for students who are engaged in research activity, who are interested in pursuing research, either fundamental, scientific research, or applied research, either way, doesn't matter. We typically look for students who have extensive research experience. So if you have a research paper published, that's great then. If you at least participated in undergraduate research program, that's also a very strong indicator of a strong application. If you have a master's degree, that's always considered in that application. Every year we admit quite a number of students from India across the country, a lot of institutions. This past year, we just finished one cycle of admission. I think this year we are welcoming 5 students from India joining our class in the fall. So that's 5 out of around 42 students of the incoming class. What else? So when students join, they go through what we call the rotation program. So you join in the fall around August, and there's a training to TA to get used to the new environment, culture, to familiarize yourself with with all the new institution, orientation from international student office and so forth. And then there will be 4 months of rotation during which you spend about 4 weeks in a research lab. And you're not committed to that research program, you just come in and get a sense of what the research is about. You got to know the students, you got to know the professor, whether it's a nice professor or harsh professor, what their expectations are. You got to know the students in the group, what kind of future colleagues you're going to work with. And certainly you will work on either work on a small project, or you work on just shadow another graduate student and get a sense of their life. Okay, so you do that for 3 different research groups, and by the end of the fall term, you got to decide which group you want to join, and then the professor then decide whether they accept you. So it's a two-way selection. Okay. But most students by this time, by the end of the fall term of every year, they will pick a research group. They will start to devote full-time in research, and also in the first year, pretty much every student will do TA. They're going to teach undergraduate course. A lot of those teaching are in the laboratory course. You supervise undergraduate students going through general chemistry or organic chemistry, analytical chemistry, those laboratory programs. And also, you take 4 classes in the first year, typically, and then you're done. You're done with class. With the exception of organic division, in which case you have to take 1 additional course. But most students will take 4 courses in different branch of chemistry, and then they're done with the courses. PhD is about doing research. It's not about getting A's. Well, students have to get a good grade, but usually your advisors are more interested in having you publishing papers. So by the end of the first year, we have 1 milestone for the students we call preliminary exam. Student will present oral exam to a committee. They will talk about very generically, what my research is going to be. What is the status of my research topic? So very broad discussion, introduction of themselves to the committee so that they got to know the professor's expectation. And then at the second year, end of the second year, is a more intense examination. It's called a comprehensive exam. By that time, students are expected to develop a strong research portfolio data, ideally a paper submitted or even published. Once you pass that milestone, then you'll move on to becoming a PhD candidate. You'll spend another 3 years to graduate with a PhD program, with a PhD degree. So that's pretty much the short version of the graduate program. Any questions I can entertain before we go back to the science?
You were asking about the scholarship programs we have.
Master program?
The scholarship programs.
Scholarship. Oh, scholarship, yes. So, as I said, all incoming students are supported financially, as long as you are making what we call reasonable progress, which means you get B and above for your courses. You hit those milestones, the preliminary exam, and also the comprehensive exam on time. You make progress in the lab, publish papers, writing your thesis, so on and so forth. We have fellowships within the department and also within the School of Arts and Science to provide more prestigious supports. Some of them are called Arts and Science Fellowship. There's also Mellon Fellowship. Mellon is, you may know this banker. So there's a Carnegie Mellon University. So Carnegie is one person, Mellon is another person. Those are two rich people lived in Pittsburgh 200 years ago. So we have a lot of these fellowships coming from this old money, and they are merit-based. So you have to do well in your courses, you have to do well in your research, and those are by internal competition. But even if you're not being supported by those scholarships, you still receive either teaching or research assistant support, as long as you're making reasonable progress. Any other questions I can entertain? Yes?
Good morning, sir. Sir, as a master's students transitioning into PhDs, do we need to have our niche sorted out, or as you said, we can explore different areas while we come and apply for the PhD programs?
Okay. I think you're asking a transition from master to PhD, whether you can change to a different field.
Yeah.
Yes,
Like
okay.
specialization, if we do it in a particular field in master's here, can we transition it or make it quite interdisciplinary if we are going to research, or we need to have it sorted out before that we will be going this way?
Yeah, so she's asking whether it's advisable to move from one field of research to another, from master research to a PhD research. It depends. There's a lot of individual component in it. From my perspective, I think it's a good thing. As I said, shared in my own trajectory, I moved to different research fields as I moved to the next stage of my career. Now, what is important, I think, is you need to make a good case. So how your previous experience can be leveraged in your future research, and how your intellectual curiosity are connected between the stages. So it's one thing that I want to move that new research field because what I learned here can help me and provide unique perspective, right? It's another thing saying, I worked on this for 2 years and I got tired of it. So this would present very different narratives. Any other questions? All right, you can always catch me after the meeting, and I'll be here for a week. So if you find me somewhere, you can just catch me asking random questions. Think about this: Indian government paid me, purchased me airfare, come here, and they want me to do something beneficial to you. All right. So let's go back to science. As shown on the top left, those are another couple, two images of graphene. On the left is an image acquired using atomic force microscope. This is the technique where you have a pin tapping the surface and get a sense of how high the materials are. In the middle, there's this black and white strips. The projection is not very, projectors doesn't work very well, but what you're supposed to see is a very thin membrane structure. As you see, there are a couple arrows, and those arrows indicate the presence of single-layer graphene. Now, this one is taken by transmission electron microscopy. So again, different imaging techniques, but showing all this kind of membrane structure at the nanoscale. Okay, so how those materials are made? There's actually a pretty long history. There's actually a pretty long history of trying to get graphene from graphite. People actually know for a long time that if you break graphite, which is a layered compound of many atoms, many sheets of atoms of carbon, if you break it into one single layer, there will be new properties because theoreticians can calculate this. They can calculate the electronic structure of graphene even without making them. And from the calculation, people know there will be interesting properties coming out of it. And one of them is a behavior of semi-metal transitioning from graphite, more semi-metal behavior from graphite to graphene. So back to 1999, there are two groups of people, one at Columbia and another at the University of Washington, Washington University at St. Louis. They were interested in thinking about ways to break graphene into thinner and thinner pieces until you get to the single layer. So what they did, as you see from this scanning electron microscopy images, they used a photolithography technique to create small columns of graphite. So we start from a big chunk of graphite and make it smaller. And then, in one case, so see the top two, look at this one. So what you see here is these people made small columns of graphite and they shear it using mechanical force, hoping that this shearing will produce single layer graphene. Now what they end up are actually small chunks of very relatively thick graphite pieces. And then there's another effort, similar idea, they create this small column, and then they come in with a AFM, atomic force microscope tip. This is, a very small, think about a needle, okay? Think about a needle. I think it this way. I have a column of micrometer-sized graphite. I come in and just bump it, and hoping that I can get a single layer. Now, neither worked. They just don't work as they thought. Now, it's a very rational approach. Make a small column and then just share it until I get a single layer. But in reality, it doesn't work. They can get thin flakes, but they never got a single layer. Now, what worked was a surprisingly very simple and counterintuitive approach. This is what got those two people Nobel Prize. And it's incredibly simple. And what you see here is on the top, there's a Scotch tape, this transparent tape. And what these two Nobel Prize winning scientists did in the UK was they put a piece of graphite on that tape, and then they fold the tape, open it, fold it again, open it again, fold it again, open it again, and essentially they break graphite flake into two every time they fold and open it. So they do this 10, 20, 30 times until the tape is covered with graphite flakes. And then they put that tape full of graphite pieces onto a silicon wafer. Okay. And then what happens after is to some degree scientific, to some degree religious. Because you have to massage it in some special way. Every every scientist has a different way of massaging the surface. And somehow, some of those thin flakes got transferred from that tape to the silicon wafer. And miraculously, you can get single layer graphene this way. It's very counterintuitive, but it worked very well. So if you look at this picture in the middle, this is the purplish structure I showed you earlier. And this is, some of them is a single layer graphene made entirely from a piece of tape. Now, this simple technique triggered all this research in graphene, studying its physics, very exotic physics, electronic structure, device fabrication, so on and so forth, and that eventually led to the Nobel Prize. Now, chemists come in and they look at this, they find this incredibly labor intensive. You literally spend about half an hour, and you can get 1 or 2 graphene pieces. Each piece is about 10 micrometer in size. You can study the physics, you can make one electronic device, but the material scientists look at this and say, this will never make an impact to anybody's life. So, chemists come in and they think about larger scale manufacturing technique, and this is something I felt very relevant to material scientists. There are a number of ways that people do this. In particular, I'm very interested in the exfoliation technique. This again will start from a bulk layered material, and graphite being one of them. But keep in mind that there are a lot of other layered bulk compounds in addition to graphite. Boron nitride, aluminum disulfide, and a lot of other things. Even antimony, bulk antimony is a layered compound. Phosphorus being another one. Those materials can be, because of their layer structure, they can be expanded by inserting something between the layers. Okay? And then you can imagine that insertion would weakening the van der Waals interaction between the layers. And then you can do something else to force the layers to become apart. And so that's the exfoliation. Now later people find it's actually not necessarily required to have this insertion process. Okay? So in this particular case, what people did was to insert alkali metal, potassium or lithium, and then put in water, and the production of hydrogen and other gas will expand the sheets of graphite into graphene pieces. But later people find many other ways to do exfoliation, but still thinking along the same idea of breaking a bulk material into its atomic composition sheets. So obviously the benefit is large-scale production. You are no longer limited by 1 micrometer size piece. Instead, you can talk about grams, even kilograms, even tons of material. Now people make graphene sheets on the ton scale using this approach. The quality is oftentimes a bit lower, so there are more defects. The sheet size is a little bit smaller, but because you can make this from using over large quantity, the cost is much lower. So in my view, which might be biased, the future of the application lies, a lot of those applications lies in this low-cost manufacturing process. Okay, so to give you 3 different examples of exfoliation. On the top is acid intercalation. In this case, you have graphite. You treat it with strong oxidizing acid. Acidic molecules come into the layers, and then you just heat it to high temperature. There will be thermal decomposition of those intercalated molecules that expanded the graphite lattice. And shown here are the scanning electron microscopy images of this expanded graphite structure. You see a lot of sheet-like structure, but it's difficult to see whether it's single layer or not. There's also a lot of research done in so-called graphene oxide material. This is the case where you chemically oxidize graphene, installing oxygen functional groups, and that make it amenable to essentially exfoliation in water because the whole material becomes much more hydrophilic. There'll be more of this, I'll talk more about this on the cover material side. But what I think is the most interesting, probably most impactful, is the so-called direct mechanical exfoliation approach. This is the case where you don't do anything special, you just add the bulk layer material in the solvent, just apply mechanical disruption. If that disruption is strong enough, if you pick the solvent combination the right way, or if you add some additive, oftentimes surfactants, if everything works out, you will just exfoliate into single sheets, magically. Okay. All right, so this is the least disruption to the lattice, and probably the lowest cost as well. So give you example. This is a process developed by a group in Northern Ireland, I think, Coleman group. They reported a variety of this mechanical exfoliation process. In some cases, you use a solvent that is friendly to the 2D material. In this case, it's graphite exfoliation, and they use the solvent called NMP. Okay. And this solvent has a surface tension similar to that of graphite and graphene, and that makes the solvent-solute interaction particularly amenable to stabilizing graphene flakes in the solvent. So they can get a variety of graphene flakes on the left-hand side are transmission electron microscopy images showing different graphene flakes. In the middle is UV absorption of the suspension. Basically shows that the suspension is stable even after 160 hours. Only about 10% of these flakes are being precipitated out. What is more interesting is even though this exfoliation is done in an organic solvent, now NMP is organic and is toxic, and people don't want to use organic solvents, they want to use aqueous system. What they find is that after the exfoliation, they can dilute the organic suspension with water by 100 times. So now you turn the organic suspension into aqueous suspension. So organic to water ratio is 1 to 100. Even in that condition, the suspension is very stable. You look at this second curve here. The curve behind the NP shows a little bit more precipitation, but over 160 hours, only 20% of them precipitate out, 80% still remains. To give you more strong visual view of the outcome of this exfoliation. So in the middle are a bunch of bottles of graphene suspension. And what is more amazing, remember this is done by mechanical disruption. You can essentially use a kitchen blender to essentially create this shear force in the liquid. If you just blend it fast enough, it will break the graphene pieces into small flakes. And they were able to make graphene pieces using this approach on the tens of gram scale per batch. Imagine you can just go to a kitchen, get your blender, add the water, surfactant, and graphite powder, and you can make graphene out of this very simple setup. All right, so this is the case where you can make graphene, but a lot of this graphene are not single layer. Okay? There are a few layers of graphene, so they're still very useful in a lot of applications, especially related to coding related to energy storage, related to electrochemistry or even sensing. But for many other applications, people actually prefer a single layer graphene, and in this case, it's not going to work out. If you look at the figure, let's see. Let me see if I can have my. Okay. Oops. If you look at the distribution here, in the top middle, to the right of the photos, that's the distribution of layer thickness. So you do see some significant fraction of single layer, but the average layer numbers on the order of 5 to 10 layers per graphene flake. So still, on average, pretty thick flakes. And also, on the bottom, you see the Raman spectrum of the sample. I'm going to talk about Raman a bit more later, but the take-home message here is there's a very strong peak labeled as D. You may notice there's a DP. And what that DP indicates is there's a lot of defects in the graphene sample. Okay. So you can get decent graphene sample, but their quality is not that high. Now, coming a different approach. This approach is called chemical vapor deposition. This one is, to some degree, exactly the opposite of everything I just talked about in exfoliation. Okay, so in exfoliation, you got very low cost production. Okay. Chemical vapor deposition is almost the opposite. It's very expensive. Okay. Exfoliation also produces a lot of material, grams, kilograms, tons. Chemical vapor deposition produces just a single layer of sheets, a very small amount, but it produces very high quality material. Okay. So what happens in the chemical vapor deposition is you have a furnace in the middle, and there's also a substrate, usually metal. And the two most common substrates used in graphene synthesis is copper or nickel, or some alloy of those metals. So during this process, you heat up the metal to about 1,000 degrees Celsius, and you flow precursor gas. And the most common precursor gas is methane, and mixed with hydrogen. So you heat it up to about 1,000 degrees Celsius. There's a decomposition of methane in the gas phase, and there will be some kind of process happening magically on the metal, and eventually you got a coating of single layer graphene on those metals. On the bottom are scanning electron microscopy image. On the left hand side, you see this dark side is the copper substrate coated with nucleation sites of graphene. You see this small triangle, and that's a signature of graphene nucleation site because of the inherent crystal symmetry of graphene is 6-fold and 3-fold. So you see this nucleation growth of graphene domain on the copper. On the right hand side, you see a very faint, it's really hard to see here, but you see a very faint line across the middle of the image, and that shows the boundary between a graphene flake and the absence of graphene. So this approach can give you a large area of single layer graphene. We're talking about centimeter square, and even in some cases, much larger ones approaching meter square of sizes. You are using a continuous row of copper foil as a substrate. And those graphene are of much higher quality. They can be made almost defect-free, so no defect, and they can in some cases, they can be made into single crystalline structure. So one piece of graphene is a single crystal up to centimeter size, domain size, and that can be done by using a single crystal of copper as the substrate. And people have figured out all those tricks to grow very large single crystal copper foil, and from there to grow single crystal graphene. So how does this process work? people spend a lot of effort understanding this growth mechanism, and basically there are two different mechanisms in operation depending on what kind of metal substrate you are using. If you're using a metal that has a low solubility of carbon, copper being one of those examples, then in that case, the gas decomposition products from the methane gas, essentially the carbon radicals, they will come to the copper surface, will absorb to the surface, but they cannot dissolve into the copper lattice. So they will stay on the surface, and they will lose hydrogen and being coupled to other carbon species. So this is an absorption and growth process, shown as B. Now, if you have a metal that has a high solubility of carbon, then the decomposition products will come to the surface, and then they got dissolved into the bulk of metal. And as temperature is lowered at the end of the reaction, the carbon dissolved in the metal lattice will precipitate out to the surface. So this is a dissolution and precipitation mechanism, and that's the pathway A. And one way to differentiate those two is to use, it's a very clever experiment done by the group at UT Austin, Ruoff. What they did is they used a mixture of methane of different isotope composition. Carbon has carbon 12 and carbon 13 being two popular isotopes. If you flow regular methane, carbon 12 methane, followed by a carbon 13 enriched methane, you can get two different outcomes. In one outcome, you'll have all the carbon isotopes mixed everywhere in the same ratio. And that would happen if you have this dissolution and precipitation mechanism, because all the carbons, whether it's carbon 13 or carbon 12, they all got dissolved, and they only precipitate out at the end of the reaction. So if you flow carbon 12 methane first and carbon 13 methane later, it doesn't matter. They still got dissolved in the lattice and come out at the same time. Okay? So in that case, if you look at the Raman spectrum, you get a single peak, because remember, Raman is the vibration, and vibration would depend on the molecular atomic weight of the atoms. So if you have different isotope, you would have different, ideally you would have different frequency of vibration. But if they're all mixed together, then you will be, averaged out. However, if you have this absorption and growth mechanism, if bulk solubility is low, then whichever is being flown first, let's say the carbon 12 methane will produce carbon 12 graphene. And then if you switch to a different methane isotope, a methane with different carbon isotope, you'll get another layer, another run of carbon 13 graphene. And in this case, you'll get two peaks in the Raman spectrum instead of one. Okay. So by using this approach, people have definitively figured out the very different growth mechanism. So this is pretty much what people have been doing with graphene. Now I have to mention, people have figured out all kinds of ways of doing CVD synthesis using every imaginable precursor combination you can think of. Polymer, gas phase, even bird drop can produce graphene. Pretty much any organic species can be used as a precursor. All you needed is some kind of carbon radical, essentially, to be captured by the metal substrate, and then nucleate and grow a carbon sheet. I want to quickly transition to TMD. This is transition metal dichalcogenides. A very popular example is molybdenum disulfide, or molybdenum diselenide, or molybdenum telluride. Those are Molybdenum is the transition metal part. The chalcogenide part is sulfur, selenium, and telluride. So any combination of those two can produce, in many cases, layered compound in the bulk, and they can be either exfoliated or grown by chemical vapor deposition into single sheets. In this case, the basic growth principle is still the same. You have a high temperature environment, you have some kind of precursor, and they combine together, and you limit their growth into single layer, and then, wow, you got single layer TMD. But the chemistry is much more complicated because a lot of the precursors are not as simple as methane. Now you have two. And in particular, one of the components is a metal, and that severely limited the kind of choice you have because a lot of metal precursors are not volatile, even at pretty high temperature. By the nature of the name, chemical vapor deposition, so you have to have some kind of mechanism to transport the precursor in the vapor phase. But nevertheless, there's a significant effort put into the CVD growth of TMDs, in part because this class of material is very interesting in terms of electronic property, in terms of optical properties. So they have very bright future in nanoelectronic industry. So at this point, people can grow wafer scale TMDs, 6-inch wafer, 8-inch wafer, single layer control, and even beyond that, hyperstructure, and some examples I'm going to show in a sec. The substrate used in a lot of those growth are also copper. Again, this is a absorption and growth mechanism. The bulk solubility of most of those TMDs are pretty low in the case of bulk copper substrate. But people have used other substrates, even as simple as silicon wafer, in growing those materials. Once you grow those materials, they are on the metal substrate. In this case, it's a gold foil that has been used. And this is the case where people grow tungsten disulfide, again, transition metal, chalcogenides. And one important task here is how do you exfoliate that single layer of 2D material from the growth substrate into something else so that you can make more interesting devices. A particular challenge here is a lot of the metal substrates, they're conductive. So if you want to make electronic device, you have to move it to another substrate that is insulating. And usually this is either a plastic substrate if you're interested in doing flexible electronics, or something like a silicon wafer where you can do large scale lithography, because in that case you need a flat substrate to work with. So there's a lot of tricks being developed to exfoliate the single layer on the metal substrate. And the most common one, including in the case of graphene, remember graphene can also be grown on copper substrate. What people used to do is to simply etch away the copper. And that can be done by using a chemical etchant, iron chloride being one of them. But that is not economical in the sense that you consume the copper substrate. So people have looked at, in this case, exfoliation by electrolysis. You apply a low voltage and that produces hydrogen, and that exfoliates, creates this gap between the TMD and the metal substrate. And from there you can attach, you can also at the same time attach a flexible plastic substrate receiving the TMD. This, in a lot of cases, can be a thermal responsive plastic. And from there you can just press them together and pull them apart, and magically the interaction between TMD on the plastic substrate is stronger. And then there's additional hydrogen evolution that creates the exfoliation effect on the metal side. And by doing that, you can create, if you look at the bottom right, okay, there are four optical images, and they show very faint yellowish structure in the middle of the plastic, and the whole structure is a piece of plastic sheet. And what you see is the transferred TMD onto those plastic sheets. And you can make sensors out of this flexible substrate, you can make electronic devices out of this flexible substrate, so on and so forth. And on the left is this triangle shape, that's an atomic force microscope image showing a large domain of the TMD grown by the MO3D process. Again, the shape is related to the underlying crystal lattice. A lot of the TMDs have threefold symmetry, so when they grow, nucleate and grow, they grow according to their crystal symmetry, and oftentimes that gives you a threefold or sixfold shape. Okay, so this technique can be expanded even further, and this is a very high density information slide, but it showed an expansion of this growth technique into heterostructure. Now, think about this whole process. This is the nucleation and growth. You bring in precursors, you will grow a little bit larger. Now, if you switch to a different precursor, you can have two different outcomes. In one outcome, if you start the nucleation and the growth, but you switch before the whole surface is covered by the TMD. Then what you can do is you can start with one nucleation, you can grow a small domain, and then you grow another material outside that domain. You still have one monolayer, but you have two different material composition. So that is a lateral heterostructure. Okay? You can also do it in another way. You grow one whole monolayer of one TMD, cover the whole surface, and then you switch to a different precursor. In that case, you will grow another layer on top of the existing layer. So that is a heterostructure in a vertical direction. So you can get lateral heterostructure or vertical heterostructure. And the top left, this is a TM image showing a heterostructure starting with graphene and transition to MOS2. And you have graphene core and the lateral patch of MOS2, so this is a metallic transition into a semiconductor. And on the right-hand side, you have a lot of vertical nucleations, especially on the right bottom. You see a triangle, but inside the triangle there's an even darker tone. And there you have two different layers. In one case, it's molybdenum disulfide diselenide, and on top of it, you have tungsten diselenide. And depending on the particular electronic structure, you can have so-called type 1 or type 2 heterostructure, or even type 3 heterostructure, and those are examples shown in this bar diagram on the right-hand side, depending on how the band gap of the two materials are stacked against each other. If you have one small band gap and a larger band gap material, they are perfectly aligned in a sense. In the middle of the band gap, that's called a type 1, and that usually is a combination that's useful for energy transfer to one material. Okay. You could have a so-called type 2 where you have this staggered band gap, and that is a good combination for charge separation. You can create full excitation, but one charge comes to one material, another charge comes to another material. So solar cell come into play, come into mind in this kind of combination. But regardless, this is a very versatile technique, and can this can give you a very useful control of electronic structure and can be useful in particular nanoelectronic applications. I want to go back to the liquid exfoliation. I shared this example of using kitchen blender to produce graphene, and this is the same research group, Dr. Coleman in Northern Ireland, and in this paper they actually used kitchen blender, shown on the top left. They use this to exfoliate a variety of 2D material, including TMD, and on the photograph you see MOS2, tungsten S2, and there's also example of boron nitride. Again, you got a lot of material out of this approach. They are not entirely single layer. If you look at the layer thickness distribution, they go anywhere from 1 layer to about 10, 12 layers. But you can get a lot of stuff. If you're interested in coating, energy storage, catalysis, this is the way to go. All right, very quickly, I was told lunch is ready somewhere, so I'm not going to hold you here for too long. I want to briefly mention 2D metallic nanostructure. Now, the case of graphene is actually a so-called summer metal. The electron conductivity is actually pretty good, especially if you can dope it. But there is a lot of effort in making true metallic in the sense that you get metal atoms coming in. Okay. There are typically 2 approaches of doing this. One is so-called bottom-up approach. You can do a lot of colloidal synthesis. And on the left is one such example. You start with gold nanoparticle, spherical gold nanoparticle. And you add some iodine, and magically the nanoparticle will transform into plates. And the reason being, some of the small molecules, iodine, bromide in particular, they absorb to certain crystalline facets of gold, so that the growth along those directions are limited. Instead, they can only grow in certain other directions. And that can produce this plate structure, and there's a variety of metallic structure you can get in this approach. Silver, gold, platinum are examples I can think of right now. There's also a templated growth you can think of, where you start with some kind of a 2D template. In this case, it's graphene oxide. It's a surface that has a lot of hydrophilic oxygenated groups that can absorb and attach to metal clusters or metal atoms. And from here, if you add gold precursor and if your conditions are right, you can get 2D gold plates. And if you look at the B panel, that is a TM image of square-shaped metallic 2D sheets. There's also top-down fabrication approach, and some of this can be done using exfoliation. Example here is antimony, because bulk antimony has a layered structure to begin with, so you can use the same kind of exfoliation approach to get single layer nano sheet of antimony. Again, quite amazing. Another approach is this very mechanical in nature. You start with bulk metal. You can add some kind of sacrificial layer, and you simply compress it mechanically, layer after layer. So you do mechanical pressing, fold it, press it again, fold it, press again. You know, gold, for example, has very good flexibility, and you can do this to the point that each layer is a couple of nanometer thick. In fact, even before graphene is known, people have been working using this approach to create very thin gold sheets to the point that is semi-transparent. You can see through very thin gold sheets if they're thin enough. So I can keep talking and talking for another hour, but I think I'll skip the application side. So there are applications in nanoelectronics I want to talk about. There's also a lot of application in sensing. There's a lot of application in electrocatalysis that 2D materials can be very good for. I can probably for another lecture, maybe combine this with application of carbon materials tomorrow. So I'll stop here and be happy to answer any questions you may have. Again, there's no stupid question, there's only stupid answer. So any question you ask will put immense pressure on my mind, but I welcome that challenge. Questions?
Yes, the topic is open for discussion. Please give mic to that girl, student. I request all the participants to be attentive because there will be a quiz session also during this 5-day program and an MCQ test at the end. Qs will be held via a software which we have organized a few weeks back also. So that quiz questions as well as the questions of the MCQ test will be based on the topics covered in the lectures. So be attentive, listen to all the lectures, make your notes as well, and then be ready for the quiz as well as MCQ test. And apologies for some inconvenience during the start of this session due to the inverter issues. But now things have been settled down and the next lecture will also be very smooth. Thank you. So you are welcome to ask questions.
Sir, you mentioned that large scale production.
Mic is not on.
Sir, you mentioned that large scale production of graphene single layer leads to lower quality. So all the process of exfoliation like acid intercalation, oxidation lead to lower quality, or is there any other process that will produce good quality single layer graphene?
Can you repeat the question for her?
Sir, you mentioned that during exfoliation process, in large scale production, there will be lower quality. So all the process leads to lower quality, or is there any process resulting in good quality of graphene single layer?
I think you're asking
About the quality for during large scale production.
Right. So during large scale production using exfoliation, does all the process lead to low quality, or will there be some variation between the methods? Okay. Yes, so there is, as I said, there's a variety of different exfoliation approaches. So, for example, here I only list three, but even between those three, there's a variety of very drastic different outcomes. In particular, the oxidation, this chemical conversion of graphite to graphite oxide and then exfoliation into graphite oxide. This one, for example, typically give you the worst quality in terms of maintaining the graphene lattice because the oxygen species are incorporated chemically. Now compare that to the direct mechanical exfoliation. The direct mechanical exfoliation actually has a lot less defects inside the flake. Now, because it's a relatively small flake, so there are a lot of defects around the edge. But that is different from the defect within the flake. So to answer your question more generally, yes, the different approach would produce different quality of material, and it all depends on what is your targeted application. You have to choose the approach that fits the end user expectation.
So according to the approach, we select the method. So according to
approach we decide the method, which type of quality we need.
Correct. So the many applications will only will highlight some of those features. For example, if you are working in the case of energy storage, lithium intercalation, for example, think about lithium battery, rechargeable lithium battery. In that case, you do not care about defects that much. As long as the material is reasonably conductive, you care a lot more about availability of intercalation sites. You care about surface area, things like this. So in those cases, you may not really care exactly which exfoliation methods you use. In some other cases, you care about thickness. In that case, the oxidation-based approach may give you a lot more single layer, just because of the nature, the way it works. The direct exfoliation doesn't give you a lot single layer that much. So again, it all comes down to what your end application would need.
Thank you.
Any other question? So it depends upon the method which we are using. It also affects the quality of the product. Yes. Thank Professor Liu for this very enlightening talk, and we are closing this first session for lunch, and we'll be again here in this hall